In this video, we'll be discussing the electromagnetic spectrum and the relationship between different wavelengths and the effects it has on molecular and electronic transition. One last thing before we begin, the beginning half of this video's title is spectroscopy, but I already have a full video over that on my channel, so it will not be discussed in this video whatsoever. If you're uninformed over spectroscopy, or you haven't seen that video I've made yet, I recommend watching it first and then resuming with this one. It's only about 6 minutes long, and I do think it clarifies quite a lot about the topic. And with all that out of the way, let's get started. Starting off with a pretty simple question, what even is the electromagnetic spectrum? Simply put, this is the entire range of electromagnetic radiation which we are aware of. The actual definition of radiation is the emission of energy as an electromagnetic wave. So yes, even visible light is radiation. This electromagnetic radiation takes the form of a wave, which you can see pictured here. These waves travel at the speed of light, and they carry energy. So to summarize, the electromagnetic spectrum shows all the different types of radiation waves, which we've discovered so far. As you can see by this graphic, these waves come in different forms, and they have different properties. The property of a wave is determined by its frequency, which is just the number of complete cycles which will take place over a period of time. To keep that simple, just look at the humps and dips of our wave. If they're very close together, like they are on this side of the graph, then we're going to have a very high frequency. If they're further apart, like on this side of the graph, it's because we have a lower frequency wave. You must also know that a higher frequency wave will carry more energy. And conversely, of course, a lower frequency wave will carry less energy. We order our electromagnetic spectrum by the length of our wave, with this graph showing the lowest frequency waves on the left and the highest frequency waves on the right. We then split these waves into separate groups, and we assign each group a name. For instance, we have radio waves, we have microwaves, we have X-ray waves. You get the point. With that introduction of the electromagnetic spectrum complete, let's take a quick break to talk about photons. I promise that this will all come back together and make sense in just a minute. When we talk about waves in the electromagnetic spectrum, what are they actually made up of? Thanks to Albert Einstein, we know it to be photons. Photons are massless packets of energy which travel at the speed of light, in a vacuum of course. Each photon will have a specific energy which depends on its frequency, or its wavelength. So if we have a higher frequency or a shorter wavelength, our photons will have more energy. So imagine we're comparing two waves. This is one wave of photons, and this is another wave of photons. Of course, our higher wave up here will have a higher energy than our wave down here. Something else you need to know is that a molecule can absorb a photon. However, this only happens under very specific circumstances. If the photon's energy matches the energy difference between electron energy levels in an atom, then an atom will absorb the photon. I know this is a lot of fancy language. To clarify, the electron sublevel energy is the difference in energy between two orbitals. If a photon has this exact amount of energy, then it can hit an electron and it could promote that electron to a higher energy state. And so that's the only thing you actually have to know about molecules absorbing photons. If it happens, which only happens if the exact energy is the same, then an electron will be promoted to a higher energy level. But don't worry about comparing the photon energy versus electron sublevel energy. That'll never be expected of you in AP chemistry. All you need to be able to do is qualitatively describe why molecules will absorb or not absorb photons, and what will happen if they absorb the photons. And so I'm just going to say it one last time. If this photon energy isn't equal to the difference in energy between orbitals, it will not be absorbed. It's probably just going to phase through the atom. And so that's everything you have to know about photons. Let's go back to the electromagnetic spectrum. For the AP exam, you need to be able to identify the different groupings of energy on the electromagnetic spectrum and the types of molecular or electron transitions, also known as changes, associated with an atom absorbing that type of energy. In simple terms, if I blast an atom with microwaves, what happens to it? If I blast it with X-rays, what happens to it? Luckily, you don't need to know all 7 of these below, you only need to know 4. Let's go through each one of these now. And again, you need to know the effects this wave will have on an atom, so make sure you're memorizing this. Starting with the lowest frequency waves you have to know are microwaves. Microwaves influence molecular rotation. If we take some polar molecules such as water and we blast them with microwaves, they will begin to rotate at a much higher frequency. That's actually what's happening to your food when you stick it in a microwave. That's why it gets hot so quick. And they're the lowest frequency waves, which just means if we were to draw them, they would be very wide, like so. The next wave frequency you need to be familiar with are infrared waves. So we're now going from microwaves to a higher wavelength, infrared. So that means our waves are going to have a higher frequency. There's going to be more energy than microwaves. These are just below our range of visible light, and they're detectable as heat, as you can see by this photo I've included here. Infrared waves influence molecular vibrations. If you want to get a molecule to vibrate really fast, blast it with infrared. Next up is visible and ultraviolet light. Visible light is all the light we can see, which, as you might notice from this graph, is an extremely small part of the entire electromagnetic spectrum. Our eyes are only adept to take in the wavelengths from 400 nanometers up to 700 nanometers. And so the wavelengths of visible light and ultraviolet radiation are going to be a lot more frequent than microwave and infrared. Make sure you know that order. Both of these wavelengths will excite valence electrons to higher energy levels. Remember our example with blasting an atom with photons. Say we take an oxygen atom and we blast it with a wave of UV photons, some of its valence electrons will be promoted to a higher energy level. In fact, if enough energy is absorbed, the electrons may even be ejected completely from the atom. So visible and UV light, that's going to be promoting valence electrons to higher energy levels. And last up, we have X-rays. These are very high up on our electromagnetic spectrum. So they have a very high wave frequency, and they have a lot of energy. In fact, they have so much energy that X-rays will remove core electrons from the atom. This is what's known as ionization. This process is actually also known as photoelectron spectroscopy, which you might recognize from an earlier unit in AP Chemistry, and you might recognize if you watched my video about it before watching this one. So make sure that you remember these 4 wavelengths and their effects on molecules. Microwaves will make molecules rotate, infrared rays will make molecules vibrate, visible/UV will excite valence electrons to higher energy levels, and then our X-rays will remove our core electrons, also known as ionization. Also, make sure to remember the order of energy for these different wavelengths. Microwaves will have the least amount of energy, while X-rays will carry the most amount of energy. And then lastly, make sure to remember that thing about the photons, how atoms and electrons will only absorb photons with exactly the right amount of energy. If the photon's energy matches up perfectly with the energy gap between our electron levels, that's the difference in energy between 2 orbitals, then the photon will be absorbed. Otherwise, it will just pass through the atom. Also remember, super important to remember, that this applies to every single type of electromagnetic wave. So the photon doesn't just have to fit perfectly for your visible UV light. That rule also exists for X-rays, it also exists for microwaves, it even exists for gamma rays, infrared rays. It applies to every single type of electromagnetic wave. And again, don't ever worry about matching up these energies or calculating for any of this in your chemistry class. All you need to know is that photons will not always be absorbed, and it's because of this difference in energy. And with that being said, that's all you have to know about spectroscopy and the electromagnetic spectrum for AP Chemistry. Personally, I think this is a pretty easy unit because you really only have 1 rule and 4 different cases to memorize. If any of this didn't make sense, I recommend rewatching parts of the video. If it's still not clicking, take a break and come back after. Thank you for watching.